Hello, so we're going to review lab safety real quick and then go through some sample questions. All right, so this is just the cut and dry, the lab safety, no fun videos or anything else. But you always listen to the instructor, read the instructions, the fire extinguishers, know where they are and how to use them. What's the acronym? PASS, pull, aim, squeeze, sweep. Pull the pin, aim at the base of the fire, squeeze the trigger, and sweep from back and forth. So if your fire is right here, you want to make sure that you are going and hitting that base in its entirety to get that full extinguish ability. Pull, aim, squeeze, sweep. Always make sure everything is organized. You do not know them multiple times. I've warned people and then I see them with their lab paper. They lean over, there goes their whole lab report with the Bunsen burner. The other thing I have seen is that some Chromebooks have almost been taken out, either been knocked over because they had them near the edge, or they knocked a beaker over and we saw those chemicals getting close to the Chromebook. So make a plan, no matter what you're doing, that you're organized and that nothing is easily bumped, and then you move slowly, obviously no horseplay or anything else. PPE, personal protective equipment. So in high school labs, it'll be safety goggles always, okay, no matter what. And sometimes you'll need aprons or gloves to protect you from splashes, especially with something that would be noxious or a skin irritant. You won't be using this, but let's say we had something radioactive, then you'd use a lead apron. That's what happens at the dentist's office when they take your x-rays. A hood. This is not a hoodie, but it is a little indent or a space in the lab that has a fan that sucks out any noxious chemicals. So you've seen them a million times in the movie where they're working with this little station right through here. Okay, and then there is a fan that is taking all that noxious stuff out instead of where you are. That is a hood. Okay, why glasses rather than contacts? No matter what, you're going to have safety goggles on, but you could have some fumes get behind those safety goggles and then have a chemical reaction with the contact lenses. That would be bad. Okay, so you're having a chemical reaction right outside your eye. Hair, jewelry, clothing, same thing. You lean over, it can knock something over or catch fire. So no loose items. If you want something to fall, if something happens to fall, you definitely do not want open-toed shoes. If there's a problem at any time, you notify the teacher. You don't get in trouble for notifying the teacher, but you do get in trouble if you don't notify the teacher, because I'll have to come along and I won't know what the spill is. So I won't know the proper procedure for cleaning it up. And you did not tell me that spill was. So if I'll find out later that this happened and you did not notify me and ask the proper way to clean it up, that is how you lose lab privileges. Okay, you're always going to wash your hands after dealing with chemicals, even if you have gloves on. You wash your hands afterwards to make sure there was nothing that could eat through the glove or to come down to your actual skin. And then after everything's all cleaned up, you would still then take off the gloves and wash your hands again to make sure that you didn't have any residual chemicals on. Obviously, no eating or drinking. Wafting is what you do. So you have your chemical here and you just waft it towards you so that you're only getting a little bit of it. And that's only if they tell you to, because you could be smelling something that is dangerous. Obviously, never mix any chemicals unless you're told to do so. The one that we do a lot is acids and water. So if you have the water here, universal solvent, and you add a little bit of acid, if it splashes back at you, what's it mainly going to be? Water. That is why you always add acid to the water. So the water has the highest concentration. Acid to water, because you oughta. Okay. Again, clean up everything and then take off your personal protective equipment. So your goggles are the absolute last thing to come off after you've taken off the other things. What do you do before you take off your PPE? You got to clean up and put everything else. So you're going to wash all your dishes. If you notice there's any cracks in there, again, this is the time to notify the teacher, because if you are heating something with even a hairline crack in it, that could cause a major issue and break. So we do not ever want to heat anything that has a crack in it. If you do notice it, you let me know. If you're heating it, you just stop heating it. So most of the stuff is pretty logical about what not to do in the lab. When in doubt, ask. I don't mind if you ask 100 times. Better to ask than not to ask. When you're cleaning up, sometimes you'll have a precipitate. That means that it rained down into a solid in the bottom of the test tube. That typically cannot go down the sink. It's a solid, but it can't necessarily go in the trash either. So that'll have a labeled disposal bucket, and it'll be in the instructions. And I will also let you know where that should go. If it's a solution or a liquid, sometimes it can go down the sink, but still most of the time it's going to be in a disposal bucket. In the one particular time that you can put it down the sink, you've got to remember dilution is the solution. So you should have the running tap water while you're adding the other chemical down. And again, most of the time that is not what you would be doing. All right, so quick review of lab safety. Now let's get into some questions. We have the independent variable, the dependent variable, the controlled variable, or the IV, the DV, and the control. Here's those definitions you had back in physical science. Okay, the x-axis is where the IV is. The experimenter is changing this value. The dependent variable is what reacts to what you did, and the controlled variable is kept the same. So a student conducted an investigation to determine the effect of water temperature on the amount of sugar that dissolves. Identify the components. So when I look at the amount of water, look at that, it's all the same. So it's the control. That makes sense. If I have more water, more sugar can dissolve regardless of temperature. So it's important to keep that the same. So I'm comparing apples to apples. Temperature of sugar, okay, same thing. Let's keep all of that the same. Everything else you want to control so that you're only having minimum changes. Temperature of water. So this one is a variable. Why? Because it's increasing in temperature. And what do we notice? When we increase in temperature, the amount of sugar increased. When we increase the temperature, so the temperature of water, the experimenter changes, and it's the IV. And the sugar dissolved then is the DV. What's a nice, cool way to remember this? Dry mix, to remember where it goes, dependence on the Y, and it responds. And we manipulate the X, and that's your IV. The other way, put it in hypothesis form. If we change the water temperature, then the amount of sugar dissolves will increase with increasing temperature because of the rules of solubility of solids in water. If IV, if the effect of the water. So you can use the hypothesis to put it in that right format as well. So multiple different areas to figure it out. All right, next question. A student measured the power. So this was measured, not manipulated. So the power is going to be my DV, my dependent variable of a motor operating at different temperatures. You are changing the different temperatures. This is our IV. The student recorded a total of 11 measurements, one at each 2-degree interval. So one at 10 degrees Celsius, one at 12, one at 14, all the way up to 30. Which change in the procedure which most improved the validity of the conclusions? Increasing the number of variables. So if you increase the number of IVs or DVs, then you are going to have more variation. That's going to be harder to tell what's going on. So that is going to decrease our validity. Decreasing the range. So if we concentrated on 10 to 15 degrees, that kind of sounds like it's the right answer. But we didn't change any of our processes. We didn't make anything more accurate. We're just using less data. So that's not it. Repeating the experiment several times. Hey, if I take 5 measurements at 10 degrees. Then if I made a mistake on one of them or read the temperature wrong, that would reduce the overall answer being incorrect. So this is definitely one of them, but we're always going to read all of them because sometimes we got to pick the best one. Okay, producing a graph. So a graph, super cool for data, but that doesn't improve the validity. That just shows the validity. So C is going to be the correct answer for that one. Why is water known as the universal solvent? So when we draw water here, this guy has two lone pairs, meaning he's polar. So like dissolves like is a year one thing that you say. Polar is going to dissolve polar. Okay, so water can dissolve polar molecules. But guess what? It's so strong, it can also, polar in terms of water, can dissolve some ionics. So now it's hitting that it can dissolve polar and ionics, but not nonpolar. Because both polar and ionic have a charge. But that has a minus because it's an alkyl. So the polar might have a small delta plus, delta minus with its dipoles, and the ionic a plus minus, but it's still attracted to the unequal distribution of charge that is water. So now when I go back, water dissolves all known substances. Nope, it does not dissolve nonpolar. You need benzene or something else that's nonpolar to dissolve nonpolar. So that's not true. It dissolves only solids. So I know it dissolves solids, but can it dissolve other things? Yep, it can dissolve liquids and gases. So that is not true. It dissolves the greatest number of substances. Maybe it dissolves 2 of the 3 types. Doesn't necessarily mean greatest, so let's keep going. It dissolves substances faster than all other solvents. That doesn't make sense because a nonpolar substance wouldn't dissolve any faster unless it was in a nonpolar solvent. So our best answer, which isn't a great answer, would be C. All right, another little experiment. We have the water, the volume in the water in the pot decreases, okay, during this investigation. And why is it decreasing? Oh, we have a heater here. So this is heating up the base. So the water decreases. So what does that mean? That water in liquid form is changing into gas form here and having water vapor. And then water droplets form on the mirror, okay? They're droplets, they're liquid form. So then when it hits the mirror, it goes back to liquid. So we have a liquid going to a gas, going to a liquid. So what do we call liquid to gas? Liquid to gas could be evaporating, or we could be boiling. Gas to liquid, condensing, like when your soda sweats, that's condensing. All right, so let's look at these things. Vaporizes and then freezes. Okay, there's no solid, so it can't be freezes. Vaporizes and then condenses. Okay, maybe, but let's keep going. Condenses and then vaporizes. That's close, but it was the wrong order. Freezes, no freezes. So this one, we found that right answer. It vaporized by turning to a gas, and then when it hit the mirror, it condensed again. What is the opposite of sublimation? So we need the definition of sublimation, and that is the phase change where it goes from a solid to a gas, skipping the liquid phase. So dry ice is solid carbon dioxide. So carbon dioxide is typically a gas at room temperature. So if I pull it out of a freezer in a solid form, it's going to skip through that liquid phase because it's like, whoa, I'm way, way, way behind. I'm just going to skip being a liquid and go right to being a gas. Okay, and so that is sublimation. So the opposite would be going from a gas to a solid. So we take a gas and put it somewhere where it's super cold or it has super high pressure and it skips the liquid phase when it's changing. The name of that is deposition because it deposits that solid down. Okay, so be aware of sometimes you'll get words like antonyms from the other subject areas. Which state is the fog? Okay, so they don't mean if it's in Colorado, they mean is it a solid, liquid, a gas, or something else? And we know fog is water vapor, so this is a gas. Okay, remember state of matter, phase of matter, solid, liquid, or gas. Type of matter, your choice is pure substance or mixture. So the fog here could be a mixture, or it could just be pure water vapor, which is a compound. So just read super carefully so you don't make those mistakes. Okay, Virginia got 4 inches of snow earlier. The temperature is now increased to 40 degrees Fahrenheit. What phase change is occurring? Now, they gave you 40 degrees Fahrenheit here because they wanted you to relate to something that you knew, but they could also say do something like 25 degrees or, any of those other numbers there. They could even say 10 degrees. What are they looking for? Any number greater than 0 degrees means it's going to do what? It's going to go from the solid phase of snow and going to melt. Now, if it was something like over 100 degrees Celsius or over 212 degrees Fahrenheit, that's the boiling point. But we didn't get anywhere close to that, so we know we're still in that solid to liquid phase change, which is called melting. All right, so a student has 4 samples of ice, each an 8-ounce plastic cup. Each sample has a mass of 50 grams. Okay, so that's a control. And a starting temperature, -10 degrees. That is a control. Each sample is placed in a different room. The graph shows the original air temperature. Okay, so in room 1, 5 degrees C, room 2, 10 degrees C, room 3, 15 degrees C, room 4, 20 degrees C. That is actually going to be what we change. That's the IV. It's on the wrong scale because they are using it just as the comparison. So they changed the rooms, but we don't really have a DV here. These are both the IV. In room 1, it's 5 degrees. We didn't have anything reacting to anything else. So this is just a graph that's showing the IV. Okay, so what do they want to know? What's happening in room 4? Okay, all of these things are above 0 degrees and less than 100 degrees. So all of them are trying to change to the liquid state from the ice, the solid state. So all of these again are melting. So freezing, nope. Evaporating, nope. Condensing. So the answer has to be melting. We didn't even get to the why. It is going to melt the fastest because it has the highest temperature. If you're freezing cold and you go into a room that's 5 degrees C, you're still going to be pretty cold. If you go into a room that's 25 or room temperature, then you're going to warm up faster. If we go into a room that's 35 or 40, like 100 degrees for 40, about there, you would get warmer faster. Which of these represents the freezing point of water in correct SI units? SI, System International, or you might know it as the metric system, but the actual name would be System International. So looking at these, we're not going to look at degrees Fahrenheit because those are not the international ones. So we're between 0 degrees and -273. So the freezing point of water is at 0 degrees. This guy down here is 0 Kelvin. That's actually where we are estimating that no motion in the molecules is happening. It's so cold, but it's way below what you and I have ever or will ever be in. We can't survive in that. So while Celsius and Kelvin are both SI units, the one that represents the freezing point would be 0 degrees C. Okay, a solid has definite shape and definite volume. So if you look at that ice here, you can see that definite shape, that crystalline structure that we're getting. The water down here at the bottom, we see all those little Mickey Mouse molecules. They're pretty close together, but kind of more random than the solid, makes sense. And the gas spreads out to fit its container, and it is random, bouncing around everywhere. So it can, both the solid or both the liquid and the gas can fit their container, but the gas is going to spread out and completely fill the container. So not just like the liquid that will take that shape of the bottom of the container. The gas is going to fill the entire part every single time. All right, some more questions. So this is the periodic table, and they say, what is the shaded row called? So if you have your Virginia SOL paper, it actually gives you a lot of details on there. You can look on the key and you'll notice that there's a 1, 2, 3, 4, 5, and those things are all labeled periods, because the periodic table just means the row table of elements, just means it's organized that way. All three of these other things are the same thing. Groups or families share similar properties. We increase our atomic number as we go along our period. Now, how many protons, electrons, and neutrons does an atom of the noble gas? Okay, noble gas. So all of these groups have names. The noble gases are over here in group or column 18 or family 18. Those are your noble gases. And so the one in the shaded area is xenon. Again, if you look on the key that comes with your periodic table, 54 is going to be labeled as your atomic number. You remember that's also your nuclear charge, and it's also the number of protons. So now we have protons. On xenon, xenon is uncharged. So protons minus charge equals the electrons. 54 minus 0 equals 54. So there are also 54 electrons. That makes sense. 54 positives of the protons, 54 negative of the electrons, perfectly balanced and uncharged. The neutrons, that's the one you got to remember. It's the big number minus the small number. And so when we find that, we get that there are 77.3 neutrons when we subtract 131.3 minus 54. We can't have a third of a neutron. It's because of the average atomic mass in isotopes that we don't have a whole number here. Okay, but how do we know how many we actually need? Use sig figs. 131.3 has 1 decimal place. 54 has 0 decimal places. The rule when you're adding or subtracting is round to the least decimal places. 0 decimal places. So we either got to round down to 77 or round up to 78. It's a 0.3. So we round down to 77 neutrons. Neutrons are neutral in the nucleus with those positive protons, and that's where most of the mass is, which is why when you add up your protons and your neutrons, you get your atomic mass. Notice none of these equations are going to be on the SOL. You get that plain periodic table that we've been using this whole term, and that is it. Every single other equation, name of groups, charges, valence electrons, all that you have to have memorized. And that's all for today.